Hello again, welcome to another lesson in geometry. Today we are covering section 12-1 tangent lines. So this is our last chapter for this year. We're covering all the properties of circles, and there are lots of them. So we want to make sure that we're paying close attention, and there's a lot of memorizing in this one, so make sure you're following along and studying every night. All right, so cross out the word that does not apply to a circle here. So we have arc, that's, remember, part of a circle, okay? So that might be an arc there, a minor arc. We have circumference, that's the distance around a circle, so we're going to keep that one. We have diameter, that's the distance across the middle of a circle, segment through the center of the circle. Equilateral is for a triangle, that's the one we're going to cross out, and then radius goes from the center to the outer edge of a circle. Circle the word for a segment with one endpoint at the center of a circle and the other endpoint on the circle. That's going to be our radius. Okay. Vocabulary builder, tangent. So this is a new word for us. Okay, tangent is to a circle is a line or ray or segment in the plane of a circle that intersects the circle exactly one point. So there's the point where it intersects. Okay. And another word is tangency for noun. In the diagram AB, line AB is tangent to the circle at point B. And B is the point of tangency. So that's the point of tangency. That's where the line crosses the circle at only one time. Okay. So BA is also a tangent ray, and segment BA is also a tangent segment. Okay. So be careful. This is not a tangent segment. Okay, if we were to extend that segment, it would cross the circle more than once. All right, so other usage in a right triangle, the tangent is the ratio of the side opposite an acute angle to the side adjacent to the angle. Okay, so the ratio of the opposite and adjacent sides. All right, vocabulary. Complete each statement with always, sometimes, or never. A diameter is never going to be a tangent. Okay. A tangent in a circle have always, tangent and a circle always have exactly one point in common. Okay, so here's a circle, and then here's our tangent. The point of tangency is the one point they have in common. A radius can always be drawn to the point of tangency. So we can always draw a radius out to that point. Okay. A tangent never passes through the center of the circle. Remember, a tangent only touches the circle at one place, even if you extend it forever. Okay? And a tangent is a ray. This is going to be sometimes. Tangent could be, remember, a segment, a ray, or a line. All right, let's flip it over and check out our second page. All right, so we learned about a tangent, okay, tangent to a circle. And you could have tangent things to any curve. And you're going to use this in calculus. It's one of the bases of what you're going to learn in calculus. So learn it now and make use of it later on. Okay. So we have a couple theorems here. Our first theorem is 12-1. If a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So this is demonstrated by this red part here. So we have DF is tangent to the circle, and its point of tangency is K. And if we draw a radius from the center O of the circle to K, then that radius and the line DF will be perpendicular to each other. Okay. All right, theorem 12-2, if a line in the plane of a circle is perpendicular to the radius at its endpoint of a circle, then the line is tangent to the circle. So if a line in the plane of a circle is perpendicular to the radius at the endpoint on the circle, then the line is tangent to the circle. So it's saying, hey, here's a line. If it's perpendicular to a radius at some point, then that's a tangency line. We know that line will only cross the circle one time. Okay. And in 12-3, if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. All right, so here are two segments. BA, there's the point of tangency for our first segment. And BC, here's the point of tangency for our second segment. These two should be congruent to each other. That's just one mark there. All right. And that's going to happen no matter where we put B, as long as A and C remain tangent to the circle. Okay. All right, use the diagram at the right for exercises 4 through 6. Complete each statement. So let's erase all this stuff off our diagram. All right, theorem 12-1. If DF is tangent to circle O at point K, then we know that DF is perpendicular to OK. All right. Theorem 12-2. If DF is perpendicular to OK, then we know that DF is tangent to circle O. All right, we should put some line marks on here. So this was a line, a segment, and a line. All right, and 12-3, if BA and BC are tangent to O, okay, then we know that BA is going to be congruent to BC. All right. So if I have a point outside the circle and it's tangent to two places on the circle, then the segments formed are going to be congruent to each other. Okay. And if we have a line that's tangent to the circle, it will be perpendicular to a radius that touches that point of tangency. Or if we have a radius as perpendicular to a line at some point on the circle, then we know that line will be a tangent line. All right, those are what the three theorems say. Problem number 1, finding some angle measures here. So segment ED is tangent to circle O. What is the value of x? So we want to know what x is, but we know that DE is tangent to O. So that means that D is on the circle, and that's our point of tangency. All right. Circle the word that best describes OD. OD is going to be a diameter of our circle. It goes all the way across from one side of the circle to the other, going through the center. What relationships does 12-1 support? Circle your answer. 12-1 says that if ED is a tangent line, and then radius OD is going to have to be perpendicular to it. So OD and ED are going to be perpendicular. They're definitely not going to be parallel, and they're not going to be congruent because I can move E wherever I feel like. I just need that D to be the tangency point. Okay. So circle the most accurate description of the triangle. So this is going to be a right triangle because we have perpendicular. That means we formed a right angle there. Circle the theorem that we'd use to solve for angle or for length or angle x here, the measurement x. And we're going to use the triangle's sum theorem. Okay, the triangle sum theorem says all three angles of a triangle should always add up to 180. And we know one of them is 90 now. We know another one is 38, and we're missing the third one. Okay. Complete the model below. Sum of the angles in a triangle is 38 plus the measure of angle D plus the measure of angle E. So the sum of measures in any triangle is 180, and that's going to be equal to 38 plus D, which was 90, plus X, which is E. Okay, and then we're going to solve that for X. So we have 180 equals 38 plus 90 plus X. So if we subtract 38 and 90 to the other side, we're going to get X is 52. So the value of X is 52 degrees. Let's flip it over and check out page 3. Okay, problem number 2. What is the distance to the horizon that a person can see on a clear day from an airplane 2 miles above Earth? Earth's radius is about 4,000 miles. So the diagram at the right shows the airplane at point A and the horizon at point H. Use the information in the problem to label the distances. Okay, so let's see what we get here. We had the Earth's radius is 4,000 miles, so 4,000 is going to go here. And we know that our airplane is 2 miles above the Earth. So this distance here is going to be 2, and then the red part is still going to be 4,000. Okay. And use the justifications at the right to find the distances. So I know that OH and AH should be perpendicular. And that's because my plane this point is line AH, the line of sight from the plane, is only going to cross the circle one time. So that's a line, a tangent line to the circle, with the point of tangency being at H. And OH is a radius of my circle, and our radius at the point of tangency should always be perpendicular to the line of tangency, okay, the tangent line. All right, so by the Pythagorean theorem, we can find our missing side here. Okay, so OH squared is going to be 4,000 squared in here. Okay, and we could keep 4,000 in this spot. Okay, and then OA is going to be 4,002. That's the 4,000 for the radius plus the 2 extra the plane is above the Earth. And then we can use a calculator to help us out here. So 4,000 squared is 16 million. And 4,002 squared is 16,016,004. Okay. Then we'll subtract it over to the other side and find out that that's going to be 16,004. And then we'll square root the 16,004. Okay, to get about 125.5069, so forth. So a person can see about 120, I'm sorry, this was 126 here, so about 127 miles to the horizon from an airplane 2 miles above the Earth. Okay, so where is that 127? That 127 is this distance from the Earth where it starts to bend around, we can't see around the edge of it, to the airplane. Okay, so 127 miles. So if you're 2 miles above the Earth, you can see 127 miles in one direction. All right, problem number 3, finding a radius. What is the radius of circle O? So we don't know what length it is, but we have an X here to show it. We do have a tangent line. I know it's a tangent line because there's a right angle here. So this must be a point of tangency. Okay. And then I know some other things. I've got 6 here, and I still don't know the radius, so that's X. So write an algebraical or numerical expression for each side of the triangle. So one side of my triangle is going to be 10. The other side will be X. So there's the 10. Here's the X. And the third side is going to be X plus 6. That's the X for the radius plus the extra 6. And it is a right triangle. So circle the longest side of the right triangle here. That's going to be this one. And circle, underline the side that is opposite of the right angle. Oh, circle the longest side of the triangle and underline the side that's opposite the right angle. Well, that's going to be the same thing. Okay. So the longest side is X plus 6, and that's also the side across from the right angle. Okay. Use the Pythagorean theorem to complete the equation. So we're going to have 10 squared plus X squared equals X plus 6 squared. And then we have to solve that. So we're going to get 100 plus X squared equals, and this is the part that's a little bit tricky. You got to remember some Algebra 1 skills here. So we're going to do it the long way first. So this would be FOIL. First terms are X squared. X times 6 is 6X. That's the outside. Inside is 6 times X for 6X. And last is 36. So if I combine that, I would get X squared plus 12X plus 36. You could do a shortcut on this one because it's a perfect square. So it says square the first term. That's where the X squared came from. Squared the second term. That's where the 36 came from. Multiply your two circles together to get 6X and then double it to get 12X. Okay. Either way, you're going to get the same thing. So we'll subtract X squared to both sides. We're going to get 100 equals 12X plus 36. Subtract 36 to both sides. We're going to get 64 equals 12X. Divide both sides by 12. We're going to get 5.3 with the bar equals X. Okay. So the radius here is going to be 5.3 with the bar. And then it's no units, so we don't have anything to write there. All right, let's flip it over and look at our last page. Problem number 5, circles inscribed in polygons. So circle O is inscribed in triangle PQR. which has a perimeter of 88 centimeters. What is the length of QY? All right, so let's talk about what inscribed means again. So inscribed means the circle touches our polygon only one time for each side. Okay, so that means all three segments of the triangle, all three sides of the triangle, are tangent to our circle. All right, so by theorem 12-3, so let's talk about 12-3 again really fast. 12-3 says we have a circle, we have a point outside the circle. If we draw tangent lines to the circle on each side, then the segments created here should be congruent to each other. So PX is going to be congruent to PZ. Okay, P is a point outside of the circle, and we have two segments, PX and PZ, that are tangent to the circle, so therefore they should be congruent. The same thing for RZ and RY, and QX and QY. So since the segments are congruent, then their measure should be equal. So PX's measure should be equal to PY's measure. I'm sorry, PZ's measure. And RZ's measure should be equal to RY's measure. And QX's measure should be equal to QY's measure. So our perimeter can be found by doing PQ plus QR plus RP. So the three sides of the triangle added up. So the perimeter is also going to be equal to PX plus XQ. That's one of the sides. And then QY plus YR. That's the other side. So there's one side, two sides, and then RZ plus ZP. There's our third side. So by the segment addition postulate, you can break all the sides into their two little pieces of segments. And then we're going to use the values in the diagram and your answer to exercise 23 to solve for QY. Okay, so we knew perimeter, this is what we started with, was PX plus XQ plus QY plus YR plus RZ plus ZP. That gets us all the way around the triangle. All right, so PX was given to us. That was 15. XQ we don't know. Okay. QY we don't know. Okay. YR we know is 17. Okay. RZ is also 17. And ZP should be 15. And we also know the perimeter. Our perimeter is 88. Okay. So we can combine all of our numbers together. We're going to get 88 equals 64 plus these two things. Now these two are congruent to each other, so let's just write them as one. So we'll say 2 times X. Which one were we looking for? QY. So let's say 2 times QY. All right. So I'll subtract 64 to both sides, and I'm going to get 24 equals 2 times QY. And then I'll divide 2 to both sides, and now I know the distance of QY, which is 12. All right. So what we're doing here is we're putting the 15 here, the 17 here. We're saying, oh, I don't know that, and I don't know that, but they're equal. And then we're writing an equation for perimeter and solving for it. Okay. All right, so our lesson check down below. A classmate insists that DF is tangent to E. Explain how to show your classmate is wrong. So as always, pause the video here, try these problems yourself, and then come back and check it over. All right, welcome back. Underline the correct word or number to complete the sentence. So a tangent to a circle is going to be perpendicular to the radius. Okay, and we have perpendicular in there, right? All right, so if DF is tangent to circle E at point F, then EFD must be 90 degrees. Uh-oh, EFD is not 90 degrees. DEF is 90 degrees, so that was supposed to be a 90 degrees right there, if it was tangent. A triangle can have at most one right angle. If it has more than one right angle, then we've already used up all 180. So explain why your classmate is wrong. So a triangle cannot have two right angles. Okay, we have one here, and he wants there to be one here. So the segment is not tangent. Okay, remember, for it to be tangent, then DF must form a right angle with the radius EF. So that's not going to work for us here. All right, so this concludes our first notes on chapter 12. Check off the vocabulary you know. You should be pretty good with circle way ahead of time. Tangent was a new one. So remember, this is a line or a ray or a segment that would intersect the circle only one time. And at that point of intersection, it should be a radius that will be perpendicular to this line or segment or ray. And then we have point of tangency. That's the place where it intersects. So how well can you use tangents to find missing links? If you're not in here, you probably want to watch this video again. I know this is some new material, so this chapter you're going to want to see videos more than once.